Okay. Today we are going to study about chapter 8, which is the first chapter of our part 2. That means you have mastered part 1. So, congratulations. Many congratulations. So let's talk about diffusion. Okay? Actually, the title of the lecture in your textbook is diffusion, but I somehow have different title, but it's okay. And in nature water, let's say you have a river, and you have a kind of velocity, and which is movement of water, and also you will have dispersion, and also you will have something happening in here which we will call as maybe reaction or settling. So this too is about the physics of the system. So we'll call that as transport. The transport is actually advection and dispersion together. It means it's about the movement, okay? And this reaction can be decomposition or transformation or settling, adsorption, things like that. That is about change. And this is about chemical reaction, chemical or biochemical process. And this is about physical process. Okay? And to understand the movement of pollutant, we need to know both movement of water and reaction of water. So we call major processes in natural water, let's say rivers and lakes and estuary and oceans, and we can collectively call those as kinetics and transport. So far, we have talked about CSTR. What is CSTR? CSTR is if you have a tank and you have completely mixed system and also you have input and output. Okay? A continuously stirred tank reactor, and that's the what CSTR is standing for. But real system, our river, or our lake, and we want treat this one as a one little cell that has same concentration everywhere. That means if this is completely mixed, and we can say everywhere in here, inside the box will have the same concentration, but in reality, that may not be the case. Okay? Sometimes if you have something coming to here, you will have very high concentration here, but the concentration will be getting smaller and smaller, right? So it can, in other words, from here to there, we have different concentration. That's your case. So your systems are not chemically homogeneous means same. Homogeneous means the antonym, the opposite meaning of the homogeneous, heterogeneous. Okay? So reverse asterisk payment the custom. But we try to always kind of we want always treat or simplify our real system for our convenience. Okay, so many times we just divide our lake or river into many different cells or grid, and in here we want to assume everything in here has the same concentration. If we want a little bit more realistic situation, what you have to do, we have to just divide this one a little bit more. But we can divide this thing maybe over and over and over again, and thus we can make this cell or grid smaller and smaller. But we'll never ever be able to copy the real world. Anyway, we can approach or we can come closer to the real system, but it requires a lot of time for calculation, and we need a very high-powered computer. And even if you have high-powered computer, you need to spend a lot of time for developing system, because every computer program you have to provide input to get the output, right? So if you have very much complicated system, you have to provide every detail, because inside here, one of the example is you need to provide the elevation of bottom, right? And you need to have that. You need to actually go to the field and take the measurement, and then you have to enter those numbers to there, because this can be very steep slope, and if that is a mountainous area, and your water will move really fast. If that is very flat area, your water is going to move really slowly. And if you consider this advection part, and this kind of slope information is very much important, right? But if you have to divide this one too much in detail, and you have to provide every different point, which can sometimes be cannot be possible, can be impossible. Anyway, the basic idea about modeling is try to copy the situation as much as you can, but not too much that we cannot handle. So we have to somehow find somewhere in the middle, or optimal point. So dispersion or diffusion can be one of those try. Okay, and then let's see. Okay, diffusion, we did talk about this before. Okay, diffusion is about velocity and when we talk about flux, the diffusion was like this, and the dispersion flux was like that. We talked about that before. So now this is not totally straight for you. I hope you somehow that equations are something that you have seen before or even familiar to you. So a diffusion actually is movement of particles. From here to there, it's a kind of it's about the space, okay, per time. But if you have dispersion, and if you have some concentration, dispersion means it's about the concentration, and it's because of molecular movement or Brownian movement, and that or tendency that they want to have equal concentration with others, because eventually this is going to be spread to the whole volume that you have there. So even though I wrote it in a very long way, these two figures show you what advection or diffusion does it look like. And then I want you to have a look at your textbook, page 1. Actually, let me find that. 138. Okay, 138. So you already have it, I guess. And so that is those in figure 8.1. A is about advection, which is the figure in upper side, and the lower side is about diffusion or dispersion. Well, many people can be confused about what is difference between diffusion and dispersion. Basically, in this class, I would say there is no difference. Well, actually, there is difference. They are different, but their kind of characteristics, way to explain those behavior can be different, similar. So I want you not too much scared about that. Okay, so for diffusion, we have two different diffusion. Molecular diffusion is a Brown movement, right? Brownian movement. Like this. This is kind of random movement, right? And Brownian movement is if you have molecule. A little, let's say you have a little water jar, you have a drop of, let's say, ink. You drop the ink, and then the ink will be dancing like this, right? It's gonna be dispersed throughout the tank. And if you wait long enough time, and the color is gonna be very, if there is a blue, and that can be more light blue or some other color, maybe dark. But if this concentration is big enough, it can be darker. About if water has relatively large volume, then that blue color can be lighter and lighter. So that's the very good example of molecular diffusion. But if you have drop in here, if you have a chopstick or stir, and if you mix it together, then they will just get mixed just right at the moment. So you can shorten the time to get dispersed. This we can call a turbulent diffusion. Turbulent means it's kind of crazy movement, right? In Chinese it says crazy. It's crazy. Turbulent diffusion. So, and if we want talk about diffusion and dispersion in a separate way, this can be diffusion and this may be dispersion. So dispersion can be big. I mean, if you compare these two, this is going to be very slow, and this is going to be very fast. But in general, if you go to the river and lake or estuary, and many kind of turbulent actions are there because of wind, because of the shoreline or the bottom, and they can have a kind of eddy motion all the time. So that can act as a kind of mixing effect for you. So in that case, we will call that called as turbulent diffusion or dispersion. In general, dispersion is a lot bigger than molecular diffusion, so we can ignore this because it's maybe 1,000,000 times bigger, 100,000 times bigger, too much big. So the values of in this case we can disregard molecular diffusion. But if you are talking about some chemical reactor that does not have this kind of physical storing motion, then in that case your molecular diffusion can be very important. Sometimes very important, because if you have some chemical reaction, I don't know what that is maybe, but if you try to make some kind of good chemical medicine or agent, then in that case, if you don't have turbulent diffusion, then molecular diffusion can be very important process. Anyway, so this is gradient. Gradient is kind of different it's slope, and minimized gradient means your slope is flat. That means concentration here and there is the same, right? So that's the what is happening in this dispersion process. So we have this thing again. So in here, as I said, the vector flux is U times C, and if we think about the unit, or let's say of these two, and I may exaggerate a little bit, but it's okay. Then we can just say that this is a square. So, and eventually, what this one said is gram and meter square and sec. So, in 1 second per 1 square meter, 1 square meter, how many grams are moving through this dispersion? That's what it says. Okay. And in this case, we have velocity and concentration. Then this is about the movement of particle via velocity, and that can be expressed with this flux concept. And so far we have been talking about V dCdt equals QC something and QC something KCV, but in here QC is very important, and QC again you can say that this is A times U times C in A times U times C and KCV. This is the same as this. So, and as we said, since this one has the unit like this, and A in here, we know the area, and this, if we multiply their unit together, then we can cancel these two. So we have a gram per sec, which is mass per time, right? I would try to say that it's mass per time. When we write mass balance equation, and their unit for each term must have mass per time unit, and in here we now know mass per time, which is the multiplication of this advection flux times A. In other words, if we have system like this, let's say this is A, and we have some velocity U, and then some coming in concentration is C in, and that's what it is. That's QC in, mass per time coming in. Also, if you have something going out, and if this is U, and again this is A, if this is C, then this is your what is going out. Okay? So I want you to try to relate the terms so far that you have learned, because they are all connected together. And so we just I just show you different ways to show or present the equations. Sometimes this kind of way is good to explain the situation, and sometimes this can be good. And at this time, you may not like this, but and if you don't like that, and then you can just regard this as, okay, this is divided by Q divided by A. That's it, right? Because Q is, no, QC divided by the way. Because Q is A times U times C and A, which is something like that. Okay, so as I said, advection in, QC in, advection out, QC out, and we can write those in our mass balance equation. Again, flux is mass per area per time, and that's something we have to memorize. Okay, simple example. If a stream velocity is 1 meter per minute and total phosphorus concentration is 50 microgram per liter, and what is the amount of advective flux for Tp in this stream? What is the advective flux? Which is Ja, that is U times C, right? U now is 1 meter per minute, and C is 50 microgram per liter, and this can be converted as milligram per cubic meter like that. And then you can simply multiply those two numbers, and then come up with 50 milligram per meter square per minute. And that means in per 1 minute, in 1 meter square area, 50 milligram is moving because of velocity. Okay? So very simple. And diffusion. As I said, if you have kind of a invisible membrane, and they can move your dissolved material like that, and at time zero, in that case, you have some concentration, but as time goes by, the concentration here can move to the other place, and eventually, every concentration inside the system can be the same. Okay? That's the basic idea. And this is kind of equation. Try to express this kind of process. So, and we must say thank you for the scientist who developed this. And if you don't want to say thank you, but we should say thank you, because in this way you can take the exam, you can solve the equation, right? All right. So this is something is not about velocity, and fluid at rest. At rest means it doesn't move at all. It's just fixed place, and then it just happens. Okay. And many times we may be interested in what is the velocity of movement of material, because eventually mass was here, and some mass is getting moved away from here to there. So we have now start to see mass and more mass and more mass, but eventually they were here and they actually moved from here to there. So many times we want to know what is the movement rate, and if you have two boxes connected together like that, and if you have something that is moving, not with the velocity, because of this person, I want to have something. So what is JD? And that is delta C and delta X. And what is delta X? And that is something distance between these two usually center point. And if you have some concentration here, this is about here, and then if you have concentration here, that's about there, then we know we have concentration 1, concentration 2, this is C1, let's say C2, and we have high concentration there and low concentration there. And then we can draw a line, then this is the slope or gradient or first derivative, in other words, dc dx, right? Because slope is first differentiation. Because this is about delta, this is about delta x here, and this is about delta c. So if you want to calculate this one, this is simply delta c over delta x. And so we can assume kind of the basic power or driving force of this movement is difference in concentration. Difference in concentration. Here, their concentration different. So the mass will move from here to there. In here, their concentration are different, so they will still move to here. In here, still concentration are different and move to here. In here, you have same concentration. It's not going to move. Maybe coming and going, maybe the same. Inside there was constantly moving, but we want to say that okay, it's the same, and we don't have any. In that case, dCdt is zero because concentration is the same. So we have flat gradient, and if you differentiate the constant is zero, right? So in this case, we don't have any gradient, we don't have any slope, we don't have any first derivative. Okay, and depend on this E right here is the constant. Some place may have very big mixing. Some place have very small mixing. So we don't know. We don't know. And usually this can be measured or given to you. And so this is a constant. So if this is dispersion coefficient. Dispersion coefficient. Okay? So that is something that can be something measured or given to you. So, but in this case, we always say that okay, flux. What was the unit? Okay, this was mass about and area and time was the unit, right? But it doesn't have to be second. It doesn't have to be gram. It doesn't have to be meters square. But whatever it is, and then eventually unit of this one is has to be like that. And in here, delta C has gram per cubic meter, and delta X has meter, right? And we need to have something so that we can have this unit, okay? So unit of E has to be something that is passive to match the unit in here. Okay, then to make this one right there, what should we do? What should we do? If we rearrange this one, we can say that this is gram per power of the fourth. Okay? Then to make this same, we need I guess, things like this, so that we can cancel these two to have this one, and then we need to have second. So, in other words, my dispersion coefficient always have unit for square of length per time. It can be centimeters squared per second, or can be different. But this is length and length, and we can alternately we can express this in it like this. Okay, so now we kind of understood why do we need to have this kind of complicated looking equations. Okay, and the scientist who developed this equation, his name was Fick. So we say that this was Fick's law, and maybe first law, right? And Fick's law is about dispersion, and since we know that dispersion is about the slope between neighbor cells together, and it's about distance, it's about the difference, right? So that's why you have, and it doesn't have to be round, it can be d or delta, whatever, but this is more general expression for any situation. So in this case, E is dispersion again, and this is the number that kind of tells you the characteristics of the mixing pattern in that area. The E in river, E in lake, E in ocean, they are all different. Okay? And you have to actually go out there and take the measurement to get the number. Or if you don't know, and then you just have to pay the money to get the data, or if you have a good friend, you can just buy a beer and then you'll be okay. So again, we have two diffusion. One is about the molecular activity, which is called a molecular diffusion, and the other is about the action of turbulence, and call it turbulent diffusion. In here, so we have two different diffusion. And I said too many words in here, but I just explain it again. Okay, then I said I have one molecular diffusion, which is can be diffusion number is dm, and the other is turbulent diffusion. That can be happening at the same time in here. As I said, and dm in your molecular level, and E is dispersion at the turbulent level. And let's go to figure 8.10 on page 149. Okay, and this one has many different, I don't know if I have it here or not. No, I don't have it. I think I must have somewhere. It's okay, it's okay. So, in here, we have the unit for dispersion number is centimeters squared per second. And we have 10 to the power of 8, which is the biggest, and 10 to the minus 8, which is the smallest. So the numbers in the left is about nearly diffusion, molecular level. But in here, on the right hand side, it's about nearly mixing. Okay? So we have many different dispersion numbers, and those are the samples. Okay, and if you read this book through, if you go to page 151, you have something, some graph that try to show you the effect of diffusion and the difference in velocity. I think it's a little bit confusion to you. It can cause a little confusion, but it's okay. It's okay. some number, but now eventually have everything as large E, and this one says longitudinal. And we have two different ways of movement. This is longitudinal, and there can be different movement, and this is lateral. This is it's a little bit difficult to explain in English because it's already there, and so I have to use a little Korean because it's about longitude, it's about along the length, and it's about lateral, about the width. Okay, so and as we know, there is movement along it this way, and also there is movement along it this way. Okay, and this longitudinal dispersion is a lot bigger than lateral, usually. Okay. Also, we are now talking about horizontal. Horizontal is this plane, right? What is vertical? Vertical is this way. So we have a dispersion in this way, and also, but we are now talking about in here. So dispersion in this way is a lot smaller than horizontal dispersion. Because horizontal dispersion we have a wind effect and many other effects, but vertical effect, sometimes if you have a deep enough water and the deeper part of the water, they're not moving at all. Then we just have molecular level diffusion only. Anyway, dispersion term E for turbulent flow bears a little relationship to the molecular diffusion coefficient D. So, in other words, dm is too much small, so if we just use E, that's okay. It's okay. So, in this case, it says for most environmental situations, the use of these above equations requires the estimation of dispersion coefficient. You have to measure it, in other words. Okay? And this one is addendum, and I want to just go through. And this one explains a little bit more about the figure that we have in figure 8.12. But this can make you a little bit confused, I guess. And I want you to just have a look at this. And then in here, we have difference in velocity in the channel. Okay, this is, let's say this is right hand side, this is left hand side. You are looking at your river from the sky. Okay, because of friction. But actually, there's some velocity there. But theoretically, we assume this one has a parabolic movement. And we assume the velocity at the center may be highest. But in general, when we talk about velocity, we talk about the average velocity. So if we consider every different velocity in one width, we use the concept of dispersion. You don't want to believe, but that's what that's saying. So that kind of difference in velocity can be included in your dispersion concept as well. But in here, we have been talking about dispersion, about difference in concentration in space, but all of a sudden we talk about velocity, and that is very much confusing. But anyway, that's the one way to explain the mixing effect, and because dispersion is a little bit different from diffusion, molecular level diffusion. So we can just, in conclusion, I think we can say that, well, we're talking about the average movement about dispersion. Even though there is a velocity there, and we have a kind of mixing effect in there. So we have mixing effect this way and that way. But in this case, we just have talking about this way. So mixing effect can be this regarded as dispersion. So that's the easiest way that we can understand what situation. Okay, now let's look at the figure, one more figure that is in your textbook in 142. 142. And last time we talked about that also. And in fixed load, what we are not happy about is this minus sign. And we may be wondering, why do we have to have this minus sign? But if we take a look at the movement of a mass due to dispersion, we will readily understand why this is necessary. Okay, let's assume a situation like this. This is x1, x2, and c1 and c2. We now know this one is higher, this is lower. So if we have kind of membrane, and if we'll just let them move, and we will know mass will move from here to there. This is plus direction. Okay? And in here, but we use dc/dt, dc/dx. In this case, this one has the slope is minus. So to make everything moving to the plus way, positive way, we have to multiply with minus. So that's why you have minus. Let's take a look at opposite way. If we have a situation like this, this concentration is going to move from here to there, which is the minus way, according to our the general way of express the x-axis. But this one we said, we know this one is the plus slope. And to make this move minus way or negative way, then we have to multiply minus. So this sign is automatically taking care of directional movement of your mass. Okay? So that's why we need minus. So now we understand, okay, why do we need dc over dx? Actually, there was difference in dc was delta c and difference in distance is delta s. But sometimes we can talk about very small distance, and in that case we can use the form of differential equation. And this one is something that you have to measure, and minus sign is about the direction of movement. Very important. Sometimes if you get confused with this direction, then you can add the material where you have to subtract, then you can make error. Okay? So, this is the error as an example, and I think you'll be happy to find your mother tongue, which is Korean. Anyway, we have two segments, C1 and C2. We have this. What question in here is, what is the mass of mass movement due to dispersion in this case? If you have C1 is 1 milliliter per liter and C2 0.5 milliliter per liter, and you have A, which is 200 meter square, and the dispersion coefficient E is 25 kilometer square per day. And then the delta X in here is 1 kilo. Then what you have to do is you have to calculate this times A, because we will be talking about mass per time, right? Good morning. Okay, so what is this CDX? And that's the C1 minus C2. And we have 1, and the other is 0.5, and L is, we know, about 1,000. So 1.5, and this is kind of correction for the unit, and 1,000 meter, and we had, let's see, 25 times something for E, and 200, and then we'll eventually come with 2,000 500 kg per day. Or mass moving due to dispersion can be very much important. For lake situation, inside the lake, we do not have too high velocity. In that case, movement of mass due to dispersion is dominant factor. In the river, we have velocity. So movement of the movement due to direction can be dominant process in your river, but in your lake, you may have an opposite situation. So you need to solve example 8.1, and I will just leave you to have fun with that. Okay, let's move on to 8.4, which is on page 143. Okay, and you have now two systems. And actually this is the model that used somewhere in Lake Huron. And if you have a river coming in here, you have maybe bay area, you have a lake area. Let's assume we have two different segments. And lake is number one, your bay is number two. So in here, to calculate the concentration for space and time, we need to develop 내가 조용히 하면 더 잘 살겠지? 하지 마. 조는 건 되는데 자는 건 안 돼. 조는 건 아무도 못 말리죠. 안 잘라고 노력하세요. 뭐 푸시업을 하든지 더 잘라잖아. Anyway, so we have a 1 and 2. So we'll develop mass balance equation. In here, what is coming in? W1, maybe this thing right there, and then but Q2, C1 is going to be coming in. Going out, maybe Q1, C1, and then we have a KCV. So plus is this and that, and minus is this and that. Now we have something, mass exchange due to dispersion. A little bit strange looking equation. And so far we have been talking about this. And all of a sudden I start to have E prime. And those are different, right? So you may start wondering why. And if we are talking about river, that is about the distance, we have to use this one. We will use this one and we'll study about, we'll practice how to use this one later. But in here, I want to show you a little simpler way to express dispersion, mass movement due to dispersion. In here, if you take a look at this one a little bit closer, maybe we can say like that, and maybe, I don't know. If you have two different concentrations, C1 and C2, and that's the difference, delta C, right? And if we talk about A, and we can have things like this, okay? And as we look at this, C1 and C2, those are something that we have to calculate. And that's something that we are interested in. But if you take a look at E and A and delta X, those are just numbers that you have to maybe measure, right? Those are kind of field data, right? You have to just go out there and take the measurement for E, take the measurement for A, and take the measurement for delta X. Maybe you can do that in the map as well. But those are numbers. If those are every numbers, then why don't you just say like this? Right? And eventually you have to measure it, and then why don't we just measure just one thing, E prime, and then reduce our energy, our waste of energy in here. Okay? So E prime is called as Burke dispersion number. In Korean, this one is kind of 이렇게 부를 수도 있어요. 총확산계수. Burke is kind of everything, right? Burke dispersion number. And by looking at this, so we'll just think about the unit of this one, and we know this one was kind of something like this before, and this one was this before, and this one was m. So eventually, if you multiply and divide them all together, and you will have unit like this, which is the same as flow, right? In here, we know unit of flow rate is cubic meter per second, right? Okay? Cubic meter per second. And since this is a linear combination, by looking at this equation, we know every term in here has to have the same unit. So in other words, E prime C2 and Q2 C2, they must have the same unit. In other words, E prime must have the same unit with the flow rate. Now, this one is like that. Okay. This multiplication and division is this whole thing has a unit like this. Okay, now I see this cubic meter per second is the same as same unit with the cube. Okay? And then we still have problem with this minus, right? This bothers us a lot. But if you come here and then take a look at those two equations, and let's just finish with developing mass balance equation. For C2, we have something coming in and going out, and there's some plus and two minuses, and now we have dispersion. If you take a look at these two, they have the same absolute value with the opposite side. One is plus, the other minus, because this is C2, C1, and C1, C2. Now, dispersion is about difference in concentration. Okay? If this is higher, they must come from here to here. If this is higher, the mass due to dispersion must move from here to there. So see, if this one is doing like that. Okay, if C2 is like this. C2 here. Okay. C2 is higher than C1, they must come here. So they must be plus coming in. If C1 is higher than C2, then this C2 minus C1 is minus sign. So this one must be, so the whole thing, this one must be minus. So mass should move from here to there. Same thing happens in this equation as well. And if C1 is higher, C1 is higher, then this one is plus, right? So the mass is going to move this way. So this is plus. If C2 is higher, then message is going to move this one, and then the message is going to be taken away from here, so it's going to be minus. So then you have to have a kind of rule. What you can do about that. So in here, since this is the equation of C1, and since I'm the host, I'll be at the last part. That'll be nice. Since this is the equation for C2, C2 will be at the last place. If you just follow that rule, this is going to be simple. 한국말로 하면 1번식에서 자기가 주인이니까 맨 뒤로 가 있으면 됩니다. 2번식에서도 2번식이니까 주인이 제일 뒤에가 있으면 자동으로 해결됩니다. 그것은 다 이런 것들을 자동으로 다 할 수 있게 돼버렸어요. 왜? 아니면 되니까 뭐 고민할 거 없을 것 같고요. Okay, let's take a break from here and then we'll just come back.